So it's my pleasure to introduce Claude, and he's going to talk about massive Kähler geometry.
Let's see, is it possible to...
In the middle one.
So I'd like to tell you about some work I've done recently with Hajo Hein, who actually, when we wrote the paper, he was at the University of Maryland. For personal reasons, namely because his wife teaches at CCNY, he's recently left Maryland and taken a job at Fordham. I'm very glad to have him in the New York area, although I think that we should consider perhaps having him here rather than leaving him over at Fordham. So the paper just came out in Communications in Mathematical Physics. I should preface the talk with the remark about the level. This is intended as a colloquium talk. Please feel free to stop me and ask questions. The slides that I had prepared beforehand were originally for a much more technical talk, but I've tried to splice into them some kind of basic material to make this talk broadly accessible, especially at the beginning. So it's very important for me that I'm not wasting anyone's time. I'd like everyone to come away having learned something. So this work concerns a certain class of non-compact Riemannian manifolds. So remember the Riemannian manifold is a manifold where you have an inner product on the tangent space. So every tangent space can be thought of as like Euclidean space. And that varies in a smooth way from point to point. But there's an interesting class of non-compact Riemannian manifolds. And I always assume, despite the picture, that we're looking at something of a dimension at least 3. So this is a fake picture. I've drawn a 2-manifold, but it's much easier to draw a 2-manifold than a 3-manifold. And most of the manifolds that we'll be interested in will be of at least dimension 4. But a non-compact Riemannian manifold is said to be asymptotically Euclidean if, and that's abbreviated in this talk as AE, asymptotically Euclidean, if there is some compact set such that when you cut out the set, what's left over is diffeomorphic to Euclidean space minus a ball. So that would already be a mild technical assumption on the topology. That would be saying that you could add a point at infinity and make it into a compact manifold. But the specific assumption is that the metric that you're looking at in this so-called asymptotic region looks very much like Euclidean space. So the components of the metric look like the identity matrix. That would be the components of the Euclidean metric in standard coordinates, plus terms that fall off at a fast enough rate in terms of the radius. And one also needs to assume that the first partial derivatives of the metric components fall off at an appropriately fast rate. So if we were in dimension 3, I'd be saying that the saying that the metric looks like Euclidean plus terms that fall off faster than 1 over radius, square root of radius. And then when you take a derivative, you would expect, if you had something that fell off like a power of the radius, then when you took a derivative, you'd expect to have knocked off 1 power. All right, so this is a technical assumption, and why I'm assuming this will not become clear until a little bit later. But to put it bluntly, these are actually very mild fall-off hypotheses. In concrete examples, you're usually looking at things that fall off to the Euclidean metric at a faster rate than this. The last key hypothesis is about the scalar curvature, and one assumes that the scalar curvature of the manifold is an integrable function. So it's an L1. Its absolute value is integrable. So what's the scalar curvature? So if you don't know much about Riemannian geometry, these are the sorts of asides that you'll probably learn the most from. The scalar curvature is a standard invariant of a Riemannian manifold, which it's just a function on the manifold. And what it measures is how the volume of a small ball compares with the Euclidean answer. So if you're in Euclidean space, the volume of a small ball looks like a standard constant depending upon the dimension times the radius here, epsilon, to the power n if you're in n dimensions. So you can look at the ratio between the volume of a ball in the manifold as a notion of volume measure in a Riemannian manifold. You can compare the volume of a ball in the manifold to the Euclidean answer, and then when you, this turns out to have a nice expansion where the first non-trivial term has a coefficient called the scalar curvature at the center of the ball. So if the scalar curvature is positive, that's saying small balls have a smaller volume than they would in Euclidean space. And this is not the way the scalar curvature was invented. That's hence the weird coefficient there. So a metric is said to be scalar-flat if this invariant vanishes. For example, it vanishes in flat space, Euclidean space, and but a much weaker condition to say the scalar curvature vanishes one says the manifold is scalar-flat. There's another invariant which is a much stronger invariant that contains a lot more information about the geometry called the Ricci curvature. And the Ricci curvature instead compares volumes of cones rather than balls to the Euclidean answer. So if you have a very narrow cone focused, you're shooting out along GDs in a very narrowly focused cone, then the volume of the cone compared to what you would expect in Euclidean space again has an expansion, and this coefficient is called the Ricci curvature in that direction. In terms of standard, if you do know some Riemannian geometry, this coefficient is actually the Ricci curvature fed two copies of a unit vector. Okay, so a metric is called Ricci-flat if this invariant of the metric is zero. So the Ricci-flat condition, not for Riemannian manifolds, but for pseudo-Riemannian manifolds, was introduced by Einstein as an equation for the gravitational field in empty space. And that's one of the reasons why the Ricci curvature became a fashionable topic. There are other forms of the curvature, notably the sectional curvature, which contains much more information about the metric. It's a fairly weak condition to say, it's a very weak condition to say that the metric is scalar-flat, and even Ricci-flat is quite, there are lots of Ricci-flat manifolds that are not flat. And we'll see some in just a moment. All right, so I've defined an asymptotic Euclidean manifold to be one where after you cut out some compact set, you can find a coordinate system on what's left. So the metric looks like Euclidean metric plus terms that fall off fast enough at infinity, and then there's this also extra condition that the scalar curvature is supposed to be integrable, which is, if you like, these are conditions on the first, on the metric and its first derivative. This is actually a condition on the second derivative of the metric. Now, actually, the definition is a little bit more flexible than what I first indicated. Rather than just supposing that when you cut out a compact set, there's only one region that looks like Euclidean space, you could be allowed to have several different connected components of the complement of a compact set, but you require that each one has this property that you can identify it with Euclidean space, in which case, in a way that makes the metric look pretty much like the Euclidean metric. So these are called the ends of the non-compact manifold. There's a more general notion of end, but here the key point is that we're just assuming that you have a compact set, so its complement looks like a disjoint union of Euclidean spaces with balls missing. And each of these things would be called an end of the manifold. Now, for many purposes, it's useful to weaken the notion of being asymptotically Euclidean to something called asymptotically locally Euclidean. And an asymptotically locally Euclidean manifold, so I think this was invented by some physicists who were drinking beer at the time. So it's called ALE. And in fact, the abbreviation AE for asymptotic Euclidean is a back formation from this one. So, so the definition is pretty similar to what we said before, that you can cut out a compact set, and then what's left over looks like a bunch of things which are essentially Euclidean, but with one key difference. Rather than assuming that each end looks like Euclidean space minus a ball, one can consider quotients of Euclidean space minus a ball by a finite group. So this would be a group of orthogonal transformations that acts freely on the unit sphere. So that then guarantees in particular that each of these, this quotient would in fact be a manifold. It would be fair game to ask for that to be a model of one region at infinity. The group can depend upon the component. You could have some components where the group is just a trivial group and it really is asymptotically Euclidean in that region, but there could be other components where it has this kind of more conical structure. In the picture I've drawn, Euclidean space modulo, or something that looks like Euclidean space modulo a group as if it's a cone, because if I were looking at a two manifold, the way you could take R2 and mod out by a finite group of rotations, it would be making something that looks like a Dixie cup. You just think of, you slice out some sector of R2 which is 2 pi over an integer, and then glue the edges together. And that's what this picture is sort of indicating. But keep in mind that's deceptive in the sense that in higher dimensions, the object you get this way, it does not look like a cone. It's not something you could isometrically embed as a hypersurface in Euclidean space and so forth. It is in an abstract sense, a cone. It is a metric cone over a space form, whatever that means. But in terms of the behavior that you assume on the metric in each of these ends, it's exactly the same hypothesis as before. It's just that topologically, one allows infinity to be a little bit more complicated. So remember, I've assumed that the dimension is at least 3, so the key point is that if you have an end which is, if it's actually asymptotic locally Euclidean, but not asymptotically Euclidean, that's in particular saying that one of these ends is not simply connected. The group gamma, that gamma I that acts on that end, it would actually be the fundamental group of that end. It's really saying that the universal cover of the end looks like Euclidean space minus ball. So why would one consider these ALE spaces? Well, the key thing is that there are important examples of them. And this, as I said, ALE was coined by a physicist who was actually in Stephen Hawking's group at Cambridge in the late 1970s, because they had discovered some very interesting Ricci-flat manifolds which were not asymptotically Euclidean, but were asymptotically locally Euclidean, ALE. They used the term gravitational instanton rather loosely at the time, but it's now become, there's a standard meaning of this, which is very precise now. So their examples, the group, there's only one end in their examples. A Ricci-flat manifold turns out could only have one end by something called the splitting theorem, Cheever-Gromov splitting theorem that originated at Stony Brook. So there's only one end, and the fundamental group at infinity is a cyclic group, which sits. The usual way of thinking about it is it's sitting inside of SU2 in O4. But I mean, it's with respect to the reverse orientation, it would be just like scalar multiplication by a root of unity. So these so-called Gibbons-Hawking metrics are examples of what are called hyper-Kähler metrics, and that led Nigel Hitchen to discover them completely independently for other reasons rather soon after the Gibbons and Hawking paper. So here I've used this word, in particular you've heard the word Kähler twice, once in the title, and it was slipped in as part of a technical term in the last slide. This fits into one of the most important ideas in modern Riemannian geometry is that of a holonomy group. If you have a Riemannian manifold, again I've drawn it like it's a surface, if you choose a base point and you have a piecewise smooth loop at that base point, you can take a vector at the base point, in the tangent space of the base point, and drag it along the loop, trying to keep it parallel to itself. I've drawn it as if we're just taking a triangle in the northern hemisphere of the Earth and dragging it from the North Pole along a line of longitude, and then dragging it along the equator. And you would agree, you're pointing in the same direction as you do this, but when you get back to the North Pole, in fact, the vector has been rotated relative to itself. So in a Riemannian manifold, there is this notion of parallel transport. You can do it around the loop. And if you look at all of these holonomy transformations from all possible loops at a base point, it gives you a subgroup of the group of orthogonal transformations of the tangent space. It's called the holonomy group of the manifold. And it's one of the key kind of rough geometric properties of the manifold. It turns out very few groups can be holonomy groups. So, for example, one possible holonomy group would be that it could be the unitary group. So if you're in even real dimension, you define the unitary group UM to be the set of orthogonal transformations on R2M, which are also complex linear, thought of as linear transformations from Cm to Cm. In other words, when this happens, the tangent space could be thought of as a complex vector space in a rather canonical way. That means that there's a linear transformation of the tangent space initially at, let's say, at our base point, mapping itself into itself with square minus 1, which would correspond to multiplying by I. However, because we've assumed that the holonomy group is in this is in the unitary group, actually, if you now just drag that notion of multiplying by I along any path to any other point, it is well defined. It's independent of which path you chose to move it along. So this is a so-called almost complex structure, which is invariant under parallel transport. Now, that can be rewritten as saying that you have a tensor field J corresponding to an endomorphism of the tangent bundle with square minus 1, and which is an orthogonal transformation with respect to the metric. But it's also the statement that it's invariant under parallel transport corresponds to saying that its covariant derivative is identically 0. Now, this is not the way Kähler geometry was invented. In fact, many people use Kähler metrics all the time and they don't know this fact. So the usual, you can read, if you have this kind of information, you can, in particular, say, let's look at the tensor field you get by sticking a J in one slot of G, or a different way of saying it is that you can reconstruct G from another tensor field where you've stuck a J in one slot. That object turns out to be a two-form. It's skew symmetric, and it's closed in the sense that its exterior derivative is 0. In particular, it has a de Rham class, which is called the Kähler class of the metric. Now, so this Kähler was a person, right? He did something. Well, what he actually did was he said the following thing that where you would say he's stark raving mad. Let's consider Riemannian metrics that we could get by taking second derivatives of a function locally. So there's some potential function locally. You take its second derivatives, mixed partial derivatives with some d by dz's and some d by dz bars, where those are the complex coordinates. And so, and then you can build some kind of symmetric tensor field from this. Consider that kind of metric. Now, like all good mathematics, he wasn't just pulling this out of thin air. He had observed, he'd been in Italy talking to the Italian algebraic geometers. He had noticed that there was an interesting structure like this on projective space. You could induce one on an algebraic variety. But the thing that got him excited was that, so I mentioned this 2 form. The corresponding 2 form is just this. But the thing that got him excited was he discovered that I mentioned the Ricci curvature before, the Ricci tensor. The Ricci tensor of this has the same kind of form as the metric. It's just that the potential, rather than being just some arbitrary function, it's built out of the log of the determinant of the components of the metric. And so, I mean, it's very difficult actually, in general. The formula for calculating the Ricci tensor of an arbitrary metric is quite complicated. And on the other hand, Kähler had discovered that it was something very, very simple for this special class of metrics, and these had something to do with algebraic geometry. Now, from a modern point of view, we would say that that formula, what it actually is saying, is that if you look at the there's actually a closed 2 form that you get by sticking J into one slot of the Ricci tensor. It's related to the Ricci tensor the same way that this Kähler form is related to the metric. And that is a closed 2 form, and moreover, it actually represents the curvature of a certain line bundle in the manifold called the canonical line bundle. So this has, so the Ricci tensor is something very mysterious for a typical metric. I mean, I've kind of told you what it does synthetically. It's about volumes of cones and so forth, but it's not easy to calculate. It's kind of a messy formula if you were to write it down. But here, it's something simple and has a clear geometrical meaning. It has to do with when you do parallel transport in the canonical line bundle, whether that whether that has non-trivial curvature or not. If the Ricci tensor, so if the canonical line bundle is flat, that actually is the same as saying that the holonomy is in a smaller group, the special unitary group. And if that's the case, then the manifold is Ricci flat. But in fact, so here, when I write the special unitary groups, those unitary transformations that have determinant 1 over the complex numbers. Right? If you're thinking of A as a complex matrix, it has complex determinant 1. But in fact, this is an if and only if statement as long as you assume the manifold is simply connected. There's a subtlety in the non-simply connected case. It has to do with the fact that on a non-simply connected manifold, a flat line bundle would still be non-trivial and to have parallel transport with monodromy in it. But if we assume that we're on a simply connected manifold, having holonomy in the special unitary group is exactly the same as your metric being Ricci flat and Kähler. These facts were discovered by Marcel Berger in the late, around 1960s. Around 1960, and one of the key contributions that was made to the subject, Berger actually gave a complete list of the possible holonomy groups up to some examples where he wasn't sure if they occurred or not. And the next person that cleared up the field was Jim Simons, who made some important contributions to the theory of holonomy. Now, I also mentioned something called a hyperkähler metric. Hyperkähler is the requirement that the holonomy is in an even smaller group. Namely, there is a group called SPL. If the dimension is divisible by 4, you can look at your Euclidean space as a vector space over the quaternions and look at orthogonal transformations which are linear, let's say on the right, with respect to the quaternions. Remember, the quaternions are not commutative, so there's actually a distinction between something that's right linear or left linear. Choose one, say right linear. So there's a group called SPL, and this also can occur as a holonomy group. This is one where Berger, it was on his list, but he didn't believe that it could really exist. It does. It really occurs in nature. So this is a subgroup of the special unitary group, so any hyperkähler manifold is also Ricci flat Kähler. So SPL, I mean, it sits in the special unitary group, but actually in a certain way it sits there in many different ways. I mean, if you have something which is quaternionic linear, I mean, it commutes with multiplying by I, but also with respect to j, with respect to k. You could permute those and change your mind about which one is I. But so anything with this holonomy is also Ricci flat and Kähler. There's a special case, which is interesting. In dimension 4, SP1 is actually the same group as SU2. So for simply connected manifolds, Ricci-flat Kähler is the same as hyper-Kähler. But remembering that hyper-Kähler also tells you, it's not just compatible with one complex structure, it's actually compatible with an entire two spheres with different complex structures. There's a two sphere that includes I, J, and K and various combinations of them. Okay, so I told you before that, that Gibbons and Hawking had written down a lot of ALE metrics, which were actually, they didn't know it, they were hyper-Kähler. They concentrated on the fact they were Ricci-flat. When Hitchin found them independently, he was looking for things that were hyper-Kähler. And Hitchin's approach was such that it was natural to conjecture that not only would there be such metrics where the group at infinity, the fundamental group of infinity, was a cyclic group, but actually any finite subgroup of SU2 should occur in his conjecture. This conjecture was then proved by Kronheimer in 1986. That was Peter Kronheimer's thesis work. This is beautifully related to some very old mathematics due to Felix Klein. Klein had looked at C2 mod a subgroup, finite subgroup of the special unitary group. If you like, that's the same as just looking at a finite group of finite subgroup of GL2C. And notice that all of these quotients could actually be embedded in these are quotients of C2, and you can always embed them in C3 as a hypersurface. So, for example, in the case the Gibbons-Hawking case, you would have something that looked like this: quadratic term and then a higher power of one variable. The next group. So, what are these groups? SU2. It sounds very abstract. SU2 is just the double cover of SO3. That means that anytime you have a finite subgroup of SU2, it also has an image which is a finite subgroup of SO3, and people going back to the ancient Greeks have been thinking about, motions, objects that had certain symmetries. And the possibilities are the dihedral groups, and then there's a double cover of the tetrahedral group, and then there's a lift of the group of the cube, or the octahedron. It's the same group. And then there's the group that is the rigid motions of dodecahedron, and that's also the same as the group of rigid motions of the icosahedron. Those are dual polytopes. All right, so these are. Remember, this was so secret among the Pythagoreans that the first guy that let out the secret, that dodecahedron was existed, and he told that to somebody who was not a sworn member of the Pythagorean order. They dragged him out to sea and threw him over with weighted down with stones to drown. So the funny thing is that also each of these groups, and this plays an important role in Kronheimer's constructions, each of them is encoded in a Dynkin diagram. They are the Dynkin diagrams of type ADE. They come up also in Lie group theory, but here it's a different link to representations of finite groups. Each node represents an irreducible representation, non-trivial irreducible representation of the finite group, and the edges represent, when you tensor that with the given representation of SU2, how does it break up? It's an amazing story. Anyway, you might notice that the Dynkin diagram associated with this secret object is the secret object E8, which was kind of a latecomer to the world. So, that's all nice. The main reason for telling you that is that here is some area where there's actually a complete classification of these objects. Each of these groups is associated, I wrote down before, a hypersurface with a singularity, but if you just change the coefficient, replace the 0 with a small constant, or actually with a polynomial of lower order, that would do too, you get a smooth submanifold, complex surface in C3, and that is the manifold in which one of these hyper-Kähler ALE metrics lives. So there's a beautiful classification there. These complex structures can be repackaged in a very interesting way. Rather than saying, well, you've got different complex structures on a hyper-Kähler manifold, you could sort of try to consider them all simultaneously, and that actually turns out to make a complex 3 manifold called the Penrose twistor space of the hyper-Kähler manifold. This naturally maps to CP1, where this parameterizes this 2-sphere represents the different complex structures. But here, this actually becomes a CP1 that's a holomorphic map. But amazingly, I found early in my career that actually this works not just for hyperkähler manifolds, it also works just for scalar-flat Kähler manifolds, complex dimension 2. So these are so-called scalar-flat Kähler surfaces. They also have twistor spaces, and you can understand the geometry of the Kähler metric in terms of the twistor spaces. So in the late 80s and early 90s, a main focus of my work was constructing such things and trying to understand their twistor spaces. And this resulted in many other examples of asymptotically Euclidean and asymptotically locally Euclidean scalar-flat Kähler manifolds. However, unlike Kronheimer's beautiful result, there is still no classification known. In the hyperkähler case, one knows exactly what the possibilities are. Here, there are still open questions. All right, so with that long prologue, I'll finally get to the topic of the lecture. I've talked about what's Kähler geometry. The other term in the, so here, this is a notion of an asymptotically locally Euclidean manifold, and I want to now define something called the mass. Again, this is something that comes out of physics. You can do the following very strange thing. Take the given coordinates and look at the following expression in the metric. You take the divergence of the metric written in components minus the gradient of its trace written in components. You then take the radial component of that vector, integrate it over a large sphere, and you take the limit of that expression as you go to infinity, and then, if you like, you can normalize it by some standard constant depending upon the dimension. So here, where am I? I'm taking the convention that one actually doesn't integrate on a large sphere. In the ALE case, I want to think of integrating on the space form. It's the hypersurface in the manifold. So that only makes a difference of the order of the fundamental group of infinity. So here we're basically taking a large sphere or a quotient of a large sphere and integrating this strange coordinate quantity and taking where it's built out of, you're taking its radial component, you're taking the Euclidean area form. This looks like it depends on the choice of coordinates. You're using this, the metric is written down as Euclidean plus something, and you're doing a bunch of stuff that use those particular coordinates. And it's not clear what this would mean. However, this is actually a number that came out of physics, and I'll explain the physics in a moment. But Bartnik and Crucial proved also in 1986, independently, that with the kinds of fall-off conditions I've just imposed, that this number is independent of the choice of coordinates. In other words, if you took another coordinate system in which the metric had similar fall-off, and you did the same computation, you would get the same number. Now, the motivation of this, it came out of general relativity. Suppose you have a 3 manifold, and you're looking at a metric which looks pretty much like the Euclidean metric, plus some small perturbations at infinity. You could imagine that that's actually the initial hypersurface in a spacetime. It's a fixed you choose some time slice of spacetime. You look at the induced metric on it, and you think the metric in, why do we call the metric G? People don't know this. It's from Einstein that G stands for gravitation, right? It's a gravitational field for the physicist. So the idea was to have a formula that reads off the apparent mass of an isolated gravitational system from what's happening far from the source. General relativity, unlike Newtonian theory of gravitation, involves nonlinear PDEs. You can't find out what the total effective mass of the system is by just integrating some local mass density. Because the equations of general relativity are nonlinear, there's a kind of self-coupling of the gravitational field. So even in empty space, you can have an effective apparent mass of a system. So this number is supposed to model if you go to the Newtonian approximation of gravity at infinity, how would this gravitational system behave? What would you think its total mass was? As an example, not just in dimension 3, you can write down in dimension n+1 a version of the so-called Schwarzschild black hole solution. So here, this is an indefinite metric, a Lorentz metric. So there's a time. This is Ricci flat in dimension n+1. But now we could just freeze time and take the induced metric on t equals 0. And so this is written in terms of a radial coordinate, and I've written it on the standard unit metric on the sphere times radius squared. If you actually take two copies of that, it glues together to make a very nice asymptotically Euclidean manifold with two ends. It's not, this would be, the induced metric is scalar-flat and asymptotically Euclidean. You might be confused by saying, well, Einstein was interested in Ricci-flat things. The Ricci-flat condition is in one higher dimension. When you restrict to the hypersurface, it's only scalar-flat. This actually is a conformally flat metric. It's rather interesting to write it down that way as a conformal rescaling Euclidean space. I won't do that. So in this particular case, there are two ends. Each end has a mass attached to it, but the mass turns out to be the same because there's actually an isometry that interchanges the ends. A priori, in general, you could have different ends with different masses. So here, this mass, whatever it is, it's somehow measuring the size of that throat. When the size of the throat goes to 0, so if you let m go to 0, this throat gets very small, and sort of in the limit, you can think of each. You're disconnecting two copies of Euclidean space. On the other hand, I showed you some Ricci-flat, or at least indicated the existence of lots of Ricci-flat A and E metrics because we defined their mass. But actually, the Ricci-flat condition turns out to imply that the mass is 0. This is another theorem of Bartnick's. So, in fact, if you laboriously computed the mass of one of those A and E metrics I mentioned, it would turn out, and does turn out, to be 0. So in fact, this is sort of the interest of this is a little bit disjoint from those metrics, although not quite. I'll come back to this. So to see a non-trivial, interesting example, let's say in real dimension 4, which has to do with Kähler geometry, I want to describe the Burns metric on the blow-up of C2 at a point. The blow-up of C2 at a point means that you replace the origin in C2 with all of the complex lines that pass through the origin. So it's this picture. It's actually the tautological line bundle over CP1. You could say it's a submanifold of C2 and CP1 where you require the CP1 direction. This vector points in the direction indicated by the CP1 area. Now, you can, since that came up as a, notice that this comes up as a submanifold of flat C2 times a round 2 sphere of some size. And it turns out when you give it the induced metric, that is scalar-flat and Kähler. It has a mass which measures the size of that 2 sphere. If you want to write it down, I indicated before, you could write down Kähler metrics in terms of second derivatives of a function. The relevant function is you take the radius squared plus 3m times the log of the radius squared. That would be on the complement of the origin of C2. All right, so this notion of mass came, when it was shared with the mathematical world, it came equipped with a conjecture. So in the conjecture, the positive mass conjecture, is that any asymptotically Euclidean manifold with non-negative scalar curvature has non-negative mass. So here, notice this is asymptotically Euclidean, not ALE, but asymptotically Euclidean. So the physical intuition is that this scalar curvature is essentially the local matter density. And the idea is that you shouldn't be able to put a lot of positive matter into the universe and end up with an effective gravitational field at infinity, which looks like the mass is negative. So physicists were very interested in this question and asked mathematicians about this. And in fact, Schoen and Yau proved this. The first version was a little bit early, but in 1979 they showed that you could prove this theorem up through dimensions 7. Their proof involves minimal hypersurfaces, and it breaks down in high dimensions because minimal hypersurfaces can have singularities. Witten gave a completely different proof using spinors in 1981. He did it just for 3 manifolds, but actually the proof, once you know it, it immediately works for any spin manifold of any dimension. Well, Hawking and Pope were among the people that were asking mathematicians about this kind of question, and they published a paper in 1978 that conjectured that this conjecture could be extended to the asymptotically locally Euclidean case too. So in 1987, I stumbled on a family of counterexamples. And these counterexamples came out of Kähler geometry. They're scalar-flat Kähler metrics on line bundles of sufficiently negative Chern class over CP1, Chern class -3 or lower. So the Burns metric was on the Chern class, -1 metric that has positive mass. The Iguchi-Hansen metric is one of the that's on the Chern class -2 line bundle. That's one of the Gibbons-Hawking metrics, and that has 0 mass. But it turns out the mass becomes negative when this line bundle has sufficiently negative Chern class. So what can one say about the mass of Kähler manifolds, and in particular, what can one say in the scalar-flat case? Well, one useful limit is that if an ALE manifold is Kähler, in fact, it can only have one end. I won't go into the proof in this talk. I don't have the time. But the main point is that in the Kähler context, you don't have to say which end you're talking about to say what the mass is, because there's only one end. All right. So in terms of our results, the first theorem is about scalar-flat Kähler metrics. And the statement is the mass of an ALE scalar-flat Kähler manifold is a topological invariant. That's to say, it's completely determined by the following data: the smooth manifold, the first Chern class of the complex structure, and the Kähler class. If you know that information, then you can determine the mass. In fact, there's actually an explicit formula, which I'll come to in a moment. So this was actually the thing we were initially aiming for in our work, because we were interested in trying to classify scalar-flat Kähler metrics, and you would like to know that a very small amount of data determines the metric. Certainly, if it determines the metric, it must determine the mass. In fact, though, there's an explicit formula for the mass just given this data. So, in particular, this makes it very easy to read off the mass of a scalar-flat Kähler metric without doing a lot of work. In those examples I mentioned, it was a laborious thing to calculate the mass. Fortunately, Mike Anderson had suggested I should do this because he knew about the paper of Gibbons and Pope, and so I calculated the mass and found out it was a counterexample. But a more recent question that was asked by Claudio Arezzo: if you have an ALE Ricci flat Kähler manifold certainly has mass 0, but he wanted to know maybe if you had an ALE scalar-flat Kähler metric for which the mass was 0, maybe the metric had to be Ricci flat. It turned out this is definitely not true, and in fact, so there are infinitely many topological types in real dimension 4 with zero mass which are not Ricci flat. In fact, I had found these examples a long time ago, but I never bothered to calculate the mass. It's now sort of really easy it takes literally 30 seconds to calculate the mass of something. All right, so the fact that, so to state the explicit formula, I have to tell you a topological fact. And it's that if you have any ALE manifold of real dimension greater than or equal to 4, this is just a topological statement. We don't really need a statement about what the metric looks like. It's just that topologically it has these ends that look like quotients of Euclidean space. So there's a notion of compactly supported de Rham cohomology. There's a complex of compactly supported forms. It has a cohomology, and it naturally maps to the ordinary de Rham cohomology. The statement is that in dimension 2, this is always an isomorphism, assuming the manifold is ALE and assuming that the real dimension is at least 4. So again, this is compactly supported cohomology. So since this is an isomorphism, let's introduce some notation for its inverse. And so if you have an ALE Kähler manifold, I want to use a club to denote the map that goes from second de Rham cohomology to compactly supported second de Rham cohomology. So what you're given a closed 2 form, you beat it over the head with a club, and then you get something that's compactly supported. Right? And now it has something, so now it defines something in compactly supported cohomology. All right, so so once we have that piece of notation, I can state the main theorem, which is on any ALE Kähler manifold, and now it's no longer assumed to be scalar-flat, on any ALE Kähler manifold of complex dimension m, the mass is given by, well, it has a term that involves the integral of the scalar curvature times a certain coefficient depending upon the dimension. Then next there is a term where there's a natural pairing between compactly supported second cohomology and closed forms in the complementary dimension. So you pair with the power of the Kähler form and integrate, if you like. And then that's times a certain factor that only depends on the dimension. So again, S here is the scalar curvature. We're integrating against the metric volume form. C1 is the first Chern class of the complex structure, and omega is the Kähler class. And here, this pairing is the natural Poincare duality between compactly supported cohomology and ordinary de Rham cohomology. So this looks like a horrific formula, maybe. It might look a little bit better if I move some of the factors over to the other side, so we just have the integral of the scalar curvature plus something else. There is for a compact Kähler manifold, there is an amazing generalization of the Gauss-Bonnet formula. Gauss-Bonnet on a surface says if you integrate the Gauss curvature, which is half of its scalar curvature, then you get a multiple of the Euler characteristic. And the Euler characteristic could be thought of as the first Chern class. So here's a formula which is true on any compact Kähler manifold. You can find the integral of the scalar curvature by pairing the first Chern class with the power of the Kähler class. And what you see here is that in the ALE case, we have a kind of anomaly. That formula doesn't work. And the mass is exactly the degree to which it does not work. So it's a boundary correction term for that formula for the scalar curvature in the compact case. Now, so this is something, this is a mass formula for any ALE Kähler manifold. But if you assume the manifold is scalar-flat, as to say the scalar curvature is 0, the integral of the scalar curvature is certainly 0. And now you get a topological formula that just involves the first Chern class and the Kähler class that computes the mass. So I've tried to make everything very user-friendly. There are a few experts here. Permit me very quickly to indicate a few of the ideas of the proof. And I'll try not to dwell on that very much. So I'm not going to try to prove this in general. It gets quite technical, but I want to look at just a very special case. Suppose that the complex dimension 2, so is 2, so it's a real 4 manifold, that the scalar curvature is identically 0, and the complex structure is standard at infinity. Now, so I'm assuming, and this turns out not to be true in general, just assume that not only can you find a real chart at infinity that makes it look like R4, but you can make it look like C2 as a complex manifold at infinity. There are examples where this is true. It doesn't always happen. All right, so we assume that the metric is Kähler, and these complex coordinates have real and imaginary parts which are harmonic functions, because a holomorphic function is harmonic. So these actually in particular give us harmonic coordinates, and when you look at this thing that you're trying to integrate, it actually simplifies to just become something that's a little more geometric. It still depends on the coordinate system, but you take the coordinate volume form, take its log, take d star of it, and with a minus sign, up to harmless terms that don't influence the mass formula. So this looks a little bit better than what I wrote down before as the definition of the mass. But now, because we're in a complex coordinate system, you can look at the one form given by d minus d bar of log of the volume density. And that's actually, d of that is actually the Ricci form. So this is so that one form has, d of that one form is the Ricci form, and this integrand here is essentially that one form wedged the Kähler form. And so you get, now in terms of having chosen some one form which, just out of infinity has the property that d of it is the Ricci form, when it gets a nicer looking formula for the mass. But I've assumed that the scalar curvature is 0, so in fact, theta wedge omega, when you, d of that is just the Ricci form wedge omega. Since the scalar curvature is 0, that's 0. This is a closed form. And so, in fact, its integral is actually independent of the hypersurface where you integrate it, as long as you keep to hypersurfaces in a fixed homology class. So this is already some major progress. This is actually sort of the first step in our work. But this is still not the mass formula I promised you. It's something more robust. It doesn't involve taking a limit. So now suppose you take a cutoff function, which is 1 at infinity and identically 0 away from the end. So it's supported just in this end, and it's identically 1 far enough out. And then we can look at the manifold with boundary you get by just cutting off at some large radius. So I said before that if you're given a closed form, you could find some compactly supported representative. Here, in this case, is an explicit way of doing it. Subtract from the Ricci form minus df theta. So that's not changing its de Rham class, but it now is producing something which is compactly supported, because out of infinity, this would look like d theta, and d theta is rho. So in fact, this is something which is a representative for a multiple of the club of C1. This should be, sorry, Kähler class, not Kähler form. So pairing with the Kähler 2 pi club C1 pairs with the Kähler class to give you the integral on this manifold with boundary. A priori, you say, well, you're supposed to integrate on the whole thing, but this is compactly supported. And now you apply Stokes' theorem. You use the fact that it's scalar-flat. This reduces to the previous integral after a little bit of work. And so, so you find, at the end of the day, that the previous simplified mass formula comes down to something that's really topological. It's just the pairing of club C1 with the Kähler class. Now, so this proof does not, this does not prove the theorem in the generality in which one claims it. So here we assume that the dimension was 2, the complex dimension was 2, the scalar curvature was 0, and the complex structure was standard at infinity. Generalizing to high complex dimension is really straightforward. You just replace the Kähler class with power. When the scalar curvature is not 0, you have to be careful. You have to put in this integral of scalar curvature to compensate, but it works pretty similarly. It turns out that in high dimensions, J is always standard at infinity. That's something we had to prove. It's also true in the asymptotic Euclidean case that J is still standard at infinity. But if it's ALE, like in the given talking metrics I looked at a moment ago, it can be non-standard at infinity, and so this is a serious point. So one way, the first way we proved it in generality involved osculating the almost complex structure by the flat one, and it turned out that we could get it so that the additional terms did not mess up the proof. There's our final version of the paper has a much better proof that involves much less regularity. In fact, use minimal regularity. All right, so how do you get this information about what does the complex structure look like at infinity? The basic idea is that you try to add a hyperplane at infinity. In the ALE case, you have to take the universal cover of the end, and then when you add, you can try to add CP, a complex hyperplane CPn minus 1 at infinity, and it turns out you have enough control on the complex structure, so that defines a smooth complex manifold after you use a sufficiently robust version of Newlander-Nierenberg. So the idea is that this is a manifold that contains CPM minus 1 with normal bundle O1, you move it around like a diagram. That's enough to tell you that your manifold looks very standard at infinity. In the asymptotic Euclidean case, so that only works though in high dimensions, you get a lot of information this way. You don't get so much dimension. You don't get any significant information that way in complex dimension 2. In the asymptotic Euclidean case, though, you can compactify M itself rather than, so you get a compact complex manifold with a CPM minus 1 whose normal bundle is O of 1. It's not so hard to prove that this defines a linear system which gives you a map to CPM. You cut back out CPM, you get a holomorphic map, a proper holomorphic map from your manifold to complex Euclidean space. That has some interesting consequences, and the first is a proof of the positive mass theorem in all dimensions, but assuming the manifold is Kähler. So this covers cases that were not known before, but only for Kähler metrics. And the technique is quite different from other known proofs. So if you take an asymptotic Euclidean Kähler manifold with non-negative scalar curvature, it has to have non-negative mass. And also, if the mass is 0, in fact, it's Euclidean space. So which is the conclusion you want in the positive mass theorem. But the proof actually shows something stronger. It proves a so-called Penrose-type inequality, which is the following. There's a lower bound for the mass that in terms of areas of some minimal submanifolds, specifically complex hypersurfaces. So if you take an asymptotic Euclidean Kähler manifold with non-negative scalar curvature, this contains a divisor, a union of a finite union of compact complex hypersurfaces expressed. So this is with integer coefficients, such that when you take, if this divisor is empty, your manifold is CM. If it's not CM, there is at least one component of this divisor. And in terms of the divisor, basically the volume of the divisor gives you a lower bound for the mass. You have positive integer coefficients on the components, and then there's some universal constant just depending upon the dimension. And you get equality if and only if the metric is scalar-flat Kähler. If your Kähler metric is scalar-flat. So where does this divisor come from? It's a so-called canonical divisor. I've said before that in the asymptotic Euclidean case, you always have this holomorphic map to Cn, which is a biholomorphism near infinity. And that means that if you just pull back the obvious M0 form, dz1 wedge dzm, then it cuts out a divisor where it vanishes. What is the set where it vanishes? It's the set of critical points for this map. So if this divisor is empty, the manifold has no critical points, and then you can prove that it's also a proper map. You can show that it's a biholomorphism. So the point is that this is a representative for the canonical class, in other words, minus C1. It's compactly supported. You can think of it as actually Poincare dual to club of minus C1. And so doing that integral just is the same as evaluating the power of the Kähler form on these hypersurfaces, and that just computes their area out to a universal constant depending on the dimension. All right, so here's the mass formula, which was the point of the talk, and you can meditate on that for a moment. I'll stop here. Any questions? I know I tried to cover too much information. Yeah.
You only find finite mass for asymptotically flat spaces, and
well, I mean, there are various points of view. You can just take this formula and declare that. I mean, you have it's a theorem in this ALE setting that computes what you would really normally call the mass. But one thing you can certainly do is say, well, this makes sense for a much larger class of spaces. In particular, for ALS spaces, this expression is well defined, and the real question is whether that invariant is good for anything. I mean, it's not there are interesting parameters that come up for the ALF solutions, like in Taub nut, there's a nut parameter, which some people call mass. It's definitely not that. It's not that because if the Kähler metric is Ricci flat, C1 vanishes, so this term is 0, and if the scalar curvature is 0, you get 0.
So shouldn't you have that parameter enter the formula for mass? I mean, I don't know. I'm asking.
Well, what I'm saying, you said, can you define mass? I mean, this formula makes sense for a much larger class of spaces. The real question is whether it's good for anything. I don't know.
So your property of the high dimensional common structure infinity standard is related to the rigidity of the equivalence invariants in high dimension?
I think it's something that's a little more I think it's something slightly different from that. It's a good question to try to connect those two phenomena. They're definitely something that's, high dimensions are quite different from complex dimension 2, and I don't see the connection right offhand, but I'm not saying that there isn't one. It's an interesting question.
Can anything like this hold for Sasaki manifolds?
Yeah, so I guess there's an interesting yoga to take a Kähler manifold and produce a manifold in of odd dimension, which is a circle bundle over the Kähler manifold, and one can certainly play that kind of game. I'm not really sure where that goes, but I mean, certainly for if you have a regular Sasakian manifold, it has a quotient which is at least a Kähler orbifold, and I guess this actually quasi-regular. So when it's regular, the quotient is actually Kähler manifold. You could play this game with orbifolds. Probably there's a sensible notion. Of course, the place where Sasakian geometry usually comes into its own is in studying positive Kähler-Einstein things and generalizing them to get odd-dimensional Einstein manifolds. So, of course, in the non-compact case, there's nothing going on. With a complete solution of Einstein's equations with positive Einstein constant is immediately compact. By Myers-Lehr, for example. So I haven't really thought about what happens in this case. You can, if you do have a Kähler class, which is an integer class, you could try playing the same game. I don't know where it goes, but it's a reasonable suggestion.
Any more questions?
Thanks for your patience, and I hope everybody learned at least something.